On exam item number 3, we have a two-span continuous beam with supports at the ends and one in the middle. So it's a statically indeterminate system. However, we've already been provided with the middle reaction. So then we're asked to provide a variety of things, including the final shear and moment diagram, the qualitative deflected shape, and the maximum displacement out here in the right-hand span, which turns out to be a much easier one to do than to find the one over in here. And I'll briefly talk about why that is. All right, so first thing we really got to do if we're going to do shear moment diagrams is we got to find the other reactions. It's a very straightforward process. Summing moments about one end will give us one reaction, and then find summing moments about the other end, or in this case, let's see here. Let's double check my symbols because it looks like things are a little goofy in terms of what's A, B, and C. I think I have them on the original exam sheet. That's A, B, and C. So I really did do it this way, but this should be, that should then be C. And that looks much better. Yeah, some moments about A gives us this far one, some moments about this end, C gets us the other one. You might say, well, you're doing a lot of fussing around. Gee, I just found one of them and then I sum forces to get the other. And yeah, you can do that, but if you make a mistake in one of them, then that's going to carry on over and you won't ever know until you actually do a bunch of work. You'll actually find out in the moment diagram that something's not right. So I always use sum of moments to find those two independently, and then I just do the simple check with sum of forces in the y that it should equal 0, and if it does, when I do that equation of equilibrium, then I know I really have gotten that correct, right? And again, when you go do the shear diagram, the fact that it was an indeterminate problem to begin with is not going to change how we create the shear diagram. Follow the point loads up. We've got a distributed load that's acting downward, so that creates a straight line segment with a negative slope in the shear diagram. Another concentrated load that is associated with the reaction pops us up above, and then we come over flat and constant because there is no distributed load in that segment, and the reaction brings us back down to 0. So just because it's indeterminate didn't change anything in that regard. Same thing with the moment diagram. We got to just follow the basic rules of the relationship between the moment and the shear, that the slope or rate of change of the moment is given to us by the shear. So big positive shear here, big negative shear here. There's at some point a 0 shear. So that tells us that we have a curved shape that is curved down, concave down. It is second order because the shear function is a straight line. We integrate shear to get to moment, so integrate a straight line gives us a second order or parabola, and this nature of what we got on the shear diagram tells us it's concave down. We know we have to have a negative moment over that interior support that should begin to be a little bit intuitive, and that's because we can anticipate what the deflected shape looks like, that with this simple load pattern, we've got loads acting downwards in this left-hand span. There are only loads there. We're going to have some sort of sagging that's going on here in the left, and this right-hand outer support is what's keeping that end out here from popping up, so it's going to have to be somehow concave down. It's being pulled back down, in a sense, into place, and that's what we found up here with the reaction to begin with. And there's got to be some transition point or in between those two. It's not over the support. The inflection point is where the moment is equal to 0, because remember that m, the moment, is equal to EI kappa. Kappa is the curvature. That's why we say where the moment is equal to 0 is where we have the inflection point. And that's happening to the left of that interior support. So we do have a little region of the frowny face curvature that extends over to the left. If we can anticipate this kind of shape to begin with, then that tells us something that we could draw very quickly over here in the moment diagram. For instance, we're going to have that negative moment that's sitting right here in that, right over the support. right? And it's got to be non-zero, because if it's zero, then we're not, weird is going to happen here, right? There's going to be bending happening out here in this right-hand segment. Just because there's no load means there's no bending going on here. And it's this additional restraint that's pulling things back down, that's causing all this to happen. That's going to shift that inflection point over to the left. All of that is building together. So we have a second order curve that comes down to here, right? And comes down to minus 27, right? You add the area on the shear diagram at the left. That takes us up to the peak. And then this area here, which is bigger than that, right? This little dashed line shows us where those two triangles are the same. And that also tells us right where the inflection point is. And then all this little area here, that little trapezoid, is what gets us from 0 moment down to the minus 27. Now, the other thing you could have thought about doing if you wanted to was to effectively do the free body diagram that you're going to see down here. But let's just pull it off to the side. And you'd have the reaction, CY, that was 2.25 kips. And you have a shear over here that's positive at 2.25 kips. And notice that that's creating a force couple that is going in a clockwise fashion. Now, positive moment is also at the left end in that clockwise fashion. Those two can't all be working in the same direction, or we won't have equilibrium. So you're going to come up with that that's going to be a negative value, and it's got to be opposite of how it's showing. And 2.25 times the 12 feet, right? Some moments about this left side if you want. And you're going to find out that's a way directly to think about that the moment is minus 27. You can get that from the moment diagram, or sorry, the shear diagram as well, right? 2.25 kips times 12 will equal 27 kip feet. That would be a positive moment change from B to C. Now we have to have 0 at the far right end, right? So if we go from right to left instead of left to right, well, in calculus integral world, that means we flip the limits on the integration. That means that positive 27, as we go from right to left, oh, well, we have to start somewhere. So we get to 0, we're going to add 27. So going right to left, we're subtracting 27, right? So that's another way to check that. And so you can get this value going all the way up and coming all the way back over that area minus all that area. It'll all get you to the same place. Okay, so there's your shear and your moment diagram. And then that qualitative deflected shape just comes from positive moment means positive curvature, right? Negative moments means negative curvature. So smiley face, frowny face. And we have to comply with the boundary conditions that at A, B, and C, those support points, there can't be any transverse displacement at any of those. So all we have to do is fit our curves in. So I just get out my French curve, and I usually do the section that is most constrained first. And that would be the right-hand side. It's all got negative curvature in there. So I would just sit there and I would plot my French curve in here where I got 0, 0, and then allow that inflection point to keep going frowny face, or not the inflection point, but allow the curvature to keep going frowny face until we get to that curvature. Do that one, and then I come along and fit in the positive curvature in there back over to the support. And that's a pretty decent qualitative deflected shape. It's sometimes really hard to get things nice and tangent right at that transition location. That can be a little bit challenging by hand, but from a qualitative standpoint, it's a pretty decent and good enough shape that I've got shown here. Now, the last thing that was asked was to find the maximum displacement in this right-hand span. And there, the key is to break this down. You've got a simply supported segment, and the thing that's causing it to bend is this bending moment, this minus 27 that's sitting here over at the left-hand side. Right? Well, wow. Hey, wait a minute. And yeah, there's some, I haven't drawn the shear that is right at that location because it's not affecting things directly, right? It's this bending moment that's causing this thing, this right-hand piece to bend. And gee, that's exactly one of the cases we have in a beam table. And that would be right out of your text. And it would be the last one, case 7. Having a little hard time getting this snuck in here. Here we go. So there's case 7, and you've got then the bending moment here at the right, and you can go and pick out the maximum deflection equation. And not only that, but it tells you where that's located. I don't have to do any derivations. The only tricky thing here is that they've got it dimensioned from the end that's opposite to the bending moment. So you do have to move things around a little bit and get them in the right location for how you want to communicate things. But the couple is here at the left, and so its value is the 27 foot. I again didn't worry about sign here because it's a simple situation. It's clear what direction things are going and that the maximum will be up. And then again, you just have to play with things. Turns out when you put the numbers in, then that the max displacement is approximately just a little over 5 feet from that middle support. Okay, now I said I would comment on why that was the easier one than the overall maximum. Well, number one, I don't know if this is the overall maximum or not. This is actually quite a really small displacement, right? So let's take a little look and compare that displacement 0.0297 to the, let's do it this way, to the beam span. So the beam span is 12 feet times 12 to get it into inches, and then divide that by 0.0297. So beam span divided by that, and that's a big number, 4848, almost 5,000. Usually we worry about if that number got smaller than 360 or 240, depending on the nature of what these loads represented. So this beam is very, very stiff for the given loads. It's not going to create much of a problem. You'll learn about that in a design class. Right? But what about this left-hand span? Why is that so much more complicated? Because after all, wouldn't the maximum displacement be right where the maximum moment is at? No, no, and oh, by the way, no. And it's not because, just even look at this over here. We had an asymmetric kind of bending or loading situation. We ended up with, therefore, an asymmetric location of where the max displacement was. In this case, it was sort of closer to where the effective applied force is on that beam span, which is this moment that's over here at the left. And we have this asymmetric moment diagram that's right there, right? Well, what about this thing? I mean, that looks symmetric. Well, it is for that portion, but that's not over the entire beam. All right, so that's a nice symmetric parabola that is over a beam that is 5.25 times 2, so 10.5 feet long, but there's an additional 1.5 feet there in that span. So maximum moment is shifted to the left, and then what that's going to tell us is that this maximum displacement is somewhere between the midspan and that maximum moment. I don't know where, maybe about halfway. I don't know where it's at, right? So you can also think about it as if I had a simply supported beam only that had a uniformly distributed load on it, and it was only 10.5 feet long, then yeah, the maximum displacement would be right there in underneath that, or at that midspan, that effective midspan, 5.25 feet. But that little simple supported span has been, in a sense, sunk down on one side, and that's going to shift to the right of that 5.25. To the right is where you're going to get that maximum displacement because you sunk that down. So wait a minute, what? How the heck would I have found that? You'd have to go in and figure out where the slope is exactly 0, and that's not going to be under the load, or under the maximum moment, I'm sorry, and it's not going to be at the midpoint of the beam. It's going to end up somewhere in between. And the other way to think about this is that the effect of this thing over here that we pulled down to keep this thing attached, when we did that, we shifted and changed the nature of the bending over here on the left. We have this little frowny face curvature that's happening just to the left of that support. And that moves around just a little bit, but it moves around where that maximum displacement is, where that 0 slope is located. And so it's a little bit of a pain to go figure out where that's at. It's not going to be an easy thing to do, because remember, slope is going to be the integration of this moment diagram divided by EI, that kappa equals m over EI, and then theta is equal to the integral of kappa. And we'd have to find out what the slope is at the far left, and then we'd have to integrate, in other words, find the area of all this stuff such that we eventually got to zero slope. That would be hard. That's not an easy thing to do. So this was a far easier question to address on the exam or even in real life about what's going on there. Now, we might ultimately expect, and it would be reasonable to expect, that the maximum displacement would be overall, would be over here on the left-hand span. It's going to be greater than this one. Why do I say that? Well, remember, moment equals EI kappa. So we've got more moment, a lot of it, this big second order curve, so a lot more area to integrate for slope changes, and bigger moment means bigger curvature. Bigger curvature is 1 over radius of curvature, so that means smaller radius. That means sharper turn, right? So this is big and gradual, and had the moment been more, this would have been sharper, right? And sharper means it's going to be bending a lot more. And that's what we've got over here effectively, is a lot of moment all over the place, a lot bigger than just what's going on in the right-hand segment. I expect, even when we account for how this kind of moves around right to the left of the support, that we're going to get a larger. How much larger? It wouldn't surprise me if this were maybe twice as much over here. Still pretty tiny when you're only talking about 1/100th of an inch in a difference, right? Maybe it's 0.06 inches, but compared to a span of 12 foot, that's still very tiny. And I know from a design perspective that you don't yet have, but that design perspective is already telling me that we've got a very stiff beam from that kind of standpoint. If you have some very sensitive kinds of instruments, they may need that that kind of stiffness.